Hi, welcome to today's session. In today's session, we'll be solving some past paper questions on chemistry. The first question that we have here is to find the general formula of alkanones. We can solve this question by picking the first option. The first option, we can draw the structural formula, which is ROCW1OH. If you do this functional group, this general formula corresponds, looking at the functional group COH, corresponds to aldehydes. And these aldehydes are known as alkanes. Let's look at the second option. It has the structural formula, double bond OR. You can put the prime, because this corresponds to, based on the functional group present, this is the functional group, the C double bond OR. This corresponds to ketones. And of course, ketones are known as alkanones. We can look at the third option, where you have RC double bond OH, because this corresponds, look at the functional group COH, this corresponds to carboxylic acids, and these are alkanoic acids. If we pick the last option that we have there, because that is the functional group RC double bond OOR, because this corresponds to esters, and esters are known as alkanoates. Okay, so if I look at this, the only one that corresponds to alkanones is the option B. The second question is talking about the constituent common to duralumin and alnico. So let's look at the name duralumin, alnico. I can pick this one first. When I say alnico, that is basically aluminium, nickel, and of course, copper. But for duralumin, of course, that is copper and aluminium, basically, of course. So the most common elements that you can have in both of them is aluminium. So we can pick this easily. Don't forget that these are called alloys. Alloys are when two or more metals are mixed together. So whenever you have two or more metals mixed together, you basically refer to them as alloys. Now we have to find the shape of the s orbital. Okay, so the understanding of orbitals will help us here. We know that the s orbital is something like this. It doesn't split at all. So basically, this shape is called spherical. Okay, but there may be need for us to understand too what is the shape for the p orbital. Okay, so the p orbital is basically seen as a dumbbell shape. Call it a dumbbell shape. Okay, or sometimes you can have something like this. So we have this, we have this. Okay, depending on the direction, since you know that p orbitals can either go along the x, y, or the z axis. So if it does that, so we call this the dumbbell shape. So that is for the p orbital. While for the d orbital, of course, this can be split into 5. Okay, so we are saying we're having a dumbbell shape, but with donuts. Okay, so when we say donut, we are talking about having something like this. Though it's a bit complex shape, just like the F, but this one we can split it into half. So we call this one double dumbbell shape, double dumbbell shape. So when I have that, I have for the SPD, the F is complex, so we don't really give it a shape. It's a very complex shape. All right, let's look at the third question. Aluminum hydroxide is used in the dyeing industry as what? So if you look at aluminum hydroxide, it is not a dye. So you can't pick dye. It doesn't disperse and is not a salt. Okay, so we know that it's not a dye. We know that it's not a salt because when we have a salt will be replacing uh, uh, metals in an acid. But this is basically a basic solution, or let me say alkaline hydroxide. So salt and dye are off it already. So we are basically what aluminum hydroxide does in the dyeing industry is to help shape. Okay, so to mold. So it's a mordant. It's a mordant. The next question is in the tincture of iodine means iodine dissolved in what? So most often, students make mistake with the state of matter of iodine. So let me quickly correct that misconception. Iodine is basically in solid state. That is the state. It's in solid state. So the iodine that is applied in the first aid treatment of wound is basically when iodine has been dissolved in a corresponding solvent. So our question here now is to find what is the solvent. So let's take a look at the option that we have. I'm going to pick this one from D. Iodine is not soluble in water, is insoluble in water. So that pick this option off. Okay. Iodine is lower than chlorine in the electrochemical series or the reactivity series. So basically, it cannot displace chlorine even from water. So that will not happen. Now, this is bromide chloride, bromine chloride. There is no way we are going to have a bromine chloride. Okay. So basically, the option that we are left with is ethanol. So iodine dissolves in ethanol to form a tincture of iodine, which is used as what? First aid treatment. Okay, first aid treatment of wounds. Now let's take a look at this question. Temporary hard water is formed when rainwater containing dissolved carbon dioxide flows over deposits of what? So we need to understand basically the reaction between carbon dioxide and other elements. But before we do that, what causes temporary hard water? Remember that temporary hard water can be removed by boiling. You can remove it by boiling. So if you are going to remove by boiling, we are basically looking at a substance that can decompose on heating. Okay, so but we can use the idea of the test for carbon dioxide, carbon dioxide, to determine which option to put here. In the test for carbon dioxide, we know that carbon dioxide reacts with lime water, okay, with lime water to form limestone plus water. Okay, so this specifically is what we call milkiness, or you say a white color appears, or you say milkiness appear. As I say, it turns lime water milky. So if that would be the case, then definitely we know that a further test for this, we say if I bubble excess of CO2 into this same solution, if I bubble excess of CO2, so we are saying this is limestone, This is water. So in this case, we can say rainwater. So if I bubble excess of CO2, we said the milkiness will disappear. Why would it disappear? We said due to the formation of soluble calcium hydrogen trisulcarbonate. So what we are saying is that if I'm having CO2 plus limestone, okay, and then of course the rainwater, or you say in the presence of water, then definitely I'm going to form calcium hydrogen trisulcarbonate 4, or you say calcium hydrogen carbonate. Okay, so this is decomposable. I can, if I heat the mixture, then definitely the milkiness will reappear. So this ability of this one to decompose on heating, so that if I heat this, I apply heat, so I'm going to form this back. And the CO2 will be given off, mind the arrow, so it will be given off as a gas. So basically, we can then say that in all of these, temporary hard water, is formed when CO2, when rainwater containing the soft CO2 flows over deposit of limestone, then you could form this, which is what causes temporary hardness. The next question said the acid anhydride that will produce a weak acid in water is what? So we first need to look at all this acid anhydride. If they react with water, SO3 plus water, okay, that is theoretically so. Don't forget that in the formation of H2SO4, in the contact process, you don't add SO3 directly to water, because that reaction is extremely exothermic, and as a result of that, we first spray SO3 with H2SO4 to form oleum before dissolving in water. Okay, don't also forget that we don't add water to acid, we add acid to water. Okay, all right. So this is H2SO4. We know that H2SO4 will undergo complete dissociation. So any acid that undergo complete dissociation, okay, that give out all the potential of hydrogen ion present in it, okay, is a strong acid. So if NO2 should dissolve in water, okay, basically I'll have HNO3. This also will undergo complete dissociation. All right, complete dissociation. So it's also a strong acid. Let's look at SO2. If SO2 should dissolve in water, of course, I'm going to have H2SO3. H2SO3. And of course, this one also will undergo complete dissociation. So we are left with only one, is SO3 2 minus. So if I pick the last option, that is CO2 plus water, CO2 plus water, and I will have H2CO3. That is what we call carbonic acid, okay? Or you say trisulcarbonate acid, which is a weak acid. So this one cannot dissociate completely. All right, so I'm going to have 2H plus CO3 2 minus. So because of this incomplete dissociation, you can see it's a reversible reaction. So CO2 is a weak acid. So when you dissolve CO2 in water, being that it's slightly soluble in water, the reaction we always want to give the CO2 back. It's just like saying carbonated water, all right, that you have in your fizzy drinks. So it's not a very weak acid. The other question we have there, the process that occurs when two equivalent forms of a compound are in equilibrium is what? So let's pick, what is isotopy? What is isotopy? When you say isotopes, we are basically talking about a situation or a phenomenon where an element can exist in different forms in the same physical state. So we have example of isotopy, let's say isotopes of hydrogen, for instance, where you have okay, I take that again. When you say isotopy, isotopy is a phenomenon where you have the same atomic number but different mass number. The same atomic number but different mass number. So this is a typical isotopy, isotopes of hydrogen, where you have, the same atomic number 1, 1, 1. But you can see the mass numbers are different. So we say these are isotopes. We have the protium, the deuterium, and the tritium. Okay, so that is isotopy. So it does not show two equivalent forms. When we say isomerism is talking about a substance having the same general molecular formula but different structural formula, having the same molecular formula but different structural formula. So it doesn't talk about equivalent forms. When you say reforming is improving to improve anti-knocking properties of petrol, to improve anti-knocking properties of petrol. So when you improve the anti-knocking properties of petrol, that is reforming. Reforming. This reforming is a qualitative test. It is different from what they call it, cracking. Cracking is when you increase the quantity of petrol. You break down heavier molecules to get lighter molecules. But reforming is when you improve the anti-docking properties. You try to improve the. So we are left with one. So when you say resonance, is basically can be seen in benzene, where you have this structure. Okay, you have this structure, and of course you have this. The bond can be here. The bond can be here. This is equivalent. Okay, you can also have it this way. All right. So instead of the bond, starting from here, I can have the bond here, a bond here, and a bond here. These two structures, or you say these two canonical structures, are in resonance such a way that I can have benzene in this form. I can actually have benzene like this. So that is because I can have two equivalent forms of the compound. All right. So we call this phenomenon resonance. The next question is saying, in the laboratory preparation of ethyl ethanoate, the water present in the mixture is removed using, okay, this is a self-answered question because in the laboratory preparation of ethyl ethanoate itself, this process takes place in acidic medium. Acidic medium. So, and the acid that is used to ensure that this happens is conc H2SO4. So that helps us very straightforward. But another idea I can add there is that when you have anhydrous calcium chloride, most often, okay, we use it to dry solid substance that may contain water. Okay, all right. But this is a liquid, so and the liquid solution is happening at acidic medium, and the acid itself that is being used is acidified by conc H2SO4. So that basically, and don't forget that concentrated H2SO4 is a drying agent. Don't forget that it's a drying agent, and it's a dry agent basically because it is hygroscopic in nature. Hygroscopic in nature. So it's being hygroscopic, it could remove water from a substance. So this question is the constant of air necessary in the roasting process are what? So we can look basically at the constituent of air. We can use this opportunity to look at the constituent of air. What are the constituents of air? So basically, air contains mainly nitrogen. Okay, that's about 78%. About 78%. We have oxygen, about 21%. Of course, we have CO2, that's about 0.03%. We have water vapor. Water vapor, of course, this is variable. We have noble gases. Noble gases is about 1%. Okay, we can say about 1%. All right. And also, of course, we also have dust particles, which is also variable. So in all of this, rusting will only take place in the presence of oxygen and water. So we can go to which one is oxygen and water, which is A. Because if you look at rusting, you can use iron, for instance, takes place, you say Fe2O3, okay, dot SH2O. So you can see, and it is iron itself originally, just iron. So we can see that only oxygen and water have been added to cause rusting. The next question is talking about the expression of equilibrium constant. So the basic idea here is that in equilibrium constant, KEQ, okay, is basically product, okay, over reactant. So if I'm to do this, then definitely what is the product? That is the RS. So in this question, this is the product. So I'm going to write that first. How do I do that? I'm going to put R, and the mole. The mole is going to be on top of it, which is M. Times the product is X, and the mole is N. So that is for the product. Then I'll come to the reactant, which is P, and the mole. The mole is X. And of course, this is Q, which is the reactant, and the mole, which is M. So I'll just look at what is corresponding. So this is RMSN, okay, RMSN, and PSQ. Okay, sorry that so we won't have this. I think that's it's normal. So that's division. So we have this one is repeated twice. So we can take it off. So we have RMSN, okay, and we have PSQY. So that makes this option a correct option for us. A given mass of gas occupies 2 dem cube at 300 Kelvin. At what temperature will its volume be doubled, keeping the pressure constant? So this has given us the key to answering this question, keeping the pressure constant. We know that it is only in gas law, Charles law, for instance, that will keep the pressure constant. Remember, Charles law states that volume is directly proportional to temperature, provided pressure is constant. Okay, provided we have the pressure constant, we said volume is directly proportional to temperature. So in this case, if that should be the case, then we are going to need a V1 over T1 equals to a V2 over T2. So let's look at the data that we have. What is our V1? You'll be given volume 1. The volume 1 is basically 2, okay? The temperature 1, fortunately for us, has been given in Kelvin, that is 300. Volume 2, how do we get volume 2? Is that at what temperature will its volume be doubled? So let's double the volume 1. That will be doubled. That's 2 times 2. Double it. So that is 4. So the original volume 1 here, I doubled it. That makes 4. So the question is, at what temperature would this happen? At what temperature would this happen? So using this relationship, I can cross multiply easily. Since I'm looking for T2, okay, so my T2 would now be equal V2, T1 over V1, okay. So what is V2? 4 times T1, which is 300, all right. Everything divided by V1, which is 2. So 2 here, can cancel this to be 2. So we can have 2 times 300. So if the volume is doubled, then definitely the temperature too will be doubled. What does this mean? We have already said that volume is directly proportional to temperature. So if volume increases, temperature will increase too. So that settles that for us. The oxidation number of iodine in KiO3 is what? So in one of our videos, we've already talked about how to calculate oxidation. You may want to check that video. All right. So this K, okay, potassium iodide, iodate. So everything will be equals to 0. All right. And remember, in that video, we talked about how to find valency. Don't forget, we said if an element is in group 1, the valency is 1, and the oxidation number will be +1. Okay. So since potassium is in that group, and we've already established that if it's in group 6, of course. Okay, let me do a sketch for you. So that's 1, 2, 3. Let's leave 4, 5, 6, 7. So basically, if element in group 1 has oxidation of +1, group 2 +2, group 3 +3. So if it's in group 5, that's -3. If it's in group 6, -2. If it's in group 7, -1. So that is how to get the oxidation quickly. So for potassium, since it's in group 1, so that the valency is 1. But don't forget, we are looking for that of iodine. So I'm representing iodine here with X, since it's look at I, so that I will not mix it up. And that of oxygen is in group 6, so that is -2. So I'm doing 3 times -2. All right. So everything equals 0. So X, basically that is 1 plus X minus 6 equals 0. My X will now be, when -6 crosses it onto positive, so that is 6 minus 1. So basically that is 5. Okay, so that's the oxidation number of iodine in this question. Which one is an isomer of C5H12? Okay, so let's look at C5H12. Basically, since this general formula correspond to the general formula CnH2n plus 2. So this is an alkane. So if it is C5, that is basically a pentane. Okay, so if it is pentane, we expect that it's going to have a carbon 5. So no matter the isomer, it must have 5 carbon and 12 hydrogen. But since we don't draw the structure here, we can get this quickly. If it can't be a butane, because butane is a C4. So if it's a C4, then it cannot meet up with C5. Okay, let's look at option A, 2-ethyl. Ethyl has 2 carbon. Butane has 4 carbon. So the total of the carbon here is a carbon 6. So definitely, since we expect that isomers will have the same molecular formula, but only different structure. So we are going to focus on on the molecular formula. We expect something that will have a C5H12. But basically, we can use the name to know the C number of carbon that should be present in that compound. So if I take a look at this now, this is basically 2-methylbutane. Okay, so this we have a C5, a butane is 4, a methyl is 1, 2-methylpropane, we have a C4. So the only one that meets number of carbon is the option C. So for this question, I don't need to draw the structure again. I can just look at the number of carbon present that corresponds. When a few drops of concentrated transaminase acid is added to an unknown sample, so you have intense yellow coloration. Of course, when you see intense yellow coloration, this basically, we call this xanthotropic test. So this is a test for protein, and the only functional group that has protein present in it is A. So test for protein. So I'll just look at the functional group that has protein present in it. So that gives us that quickly. A sample of orange juice is found to have a pH of 3.80. So how do we solve this? For us to solve this, we need to understand how to calculate pH itself. How is pH calculated? pH is calculated by finding the negative logarithm of hydrogen ion concentration. So, but now we're asked to find the hydrogen ion concentration. If I apply this, so the hydrogen ion concentration, okay, you may need your calculator here, will be, okay, so if I do this, the pH will be antilog, antilog of the pH. I say minus antilog of the pH. Okay, if I don't want to put the minus here, okay, I can say minus antilog of the pH. So that's the hydrogen ion concentration. So I just find, all I need to find is the antilog of 3.80. Okay, find the antilog of this, and that will basically give you, just press your calculator, that gives you 6.3 times 10 to the minus 4. Okay, just find the antilog and you are away there. Incomplete oxidation of ethanol yields what? We know that oxidation of ethanol will depend on what class of ethanol that we have, what class of alcohol that we have. For this one, ethanol is, let's look at the general formula of ethanol. This CH3, CH2 as the molecular formula or structural formula, CH3, CH2OH. This is the structural formula. So the CH2, the OH is attached to a carbon that has 2 hydrogen. So basically this is a primary, or you say 1 degree, primary or 1 degree alkanol. So when you oxidize a primary alkanol, you first move to alkanal, and then complete oxidation will now give us alkanoic acid. Okay, alkanoic acid. All right. So this is the first level of oxidation. But this is a complete oxidation. This one is incomplete. So all I need to do is to check which of these corresponds to alkanal. So we've established this in the first question that we solved. Can you still remember this? This is a carboxylic acid. This is RCOR. Okay. So this is a ketone. Okay. Of course, this is the same thing as this ROR. This is an ether. Okay. And of course, this is RCOH. Or is it RCOH or RCHO? Either of the two. So This corresponds to an alkanal. This corresponds to an alkanal. The salt formed from a weak acid and a strong base hydrolyzes in water to form what? So how do we solve this question? We need to have an understanding of hydrolysis. If I have a strong acid plus a strong base, the salt that is formed in solution on hydrolysis will be neutral. Now, don't mix this up with acid salt or basic salt, neutral salt. No, that's not what we are saying here. What we are saying here is that no, the salt that is formed, even when it's a normal salt, once a salt is formed between a strong acid and a strong base, that salt, if I now put it in water, it will hydrolyze to form a neutral solution, meaning that if I put litmus inside, there will not be any change in litmus. But if it is with a strong acid and a weak base, so this helps us quickly. Strong acid, strong acid. So we expect that it will be acidic. Okay. If it is a weak acid versus a strong base, so the stronger one will dominate. So it will be alkaline. I think that makes it a bit easier for us. So if I have that, then the question is a weak acid. So this is answering for us. So it's going to be an alkaline solution. So once you do this, you could use that to solve any question of this nature. The ideal gas law and equations that are true for all gases at what? Okay, so we know that at high pressure, gases tends to condense back to liquid. That's at high pressure. When you put high pressure, they turn to condense back to liquid. And we know that at very low temperature, of course, gases will turn to liquid, and if the temperature is lowered further, may even turn to solid. So for a gas to be ideal, ideal means to obey Boyle's law, Charles' law, ideal gas laws. Okay, so this will only happen at low pressure and high temperature. So the pressure is low and the temperature is high. When that happens, of course, definitely there will be a form of ideality about a gas. When change in H is negative, a reaction is said to be what? So how do we calculate enthalpy change? Don't forget that we calculate enthalpy change by looking at the energy summation of the product minus that of the reactant. So of course, if I have a negative value from here, if I have a negative value, what this is saying is that the energy of the reactant is higher than that of the product. If it is higher, then definitely there is a loss of energy because the reactant has a higher energy than the product. So that is loss of energy. And if energy is lost to the environment in the form of heat, so that is basically an endothermic reaction. But if this answer here is positive, of course, that means a gain. So we are saying that the reactant has a lower value. Let me use a value. Let's say I have 10 here, I have 20 here. So that would be a gain of energy, in the form of heat. So that would be an endothermic reaction. But if the reverse were to be the case, where I have 5 here, okay, I have 5 here, and I have 1 here. So the value will be negative, meaning that energy has been lost to the environment. So that is an endothermic reaction. Okay, in this question, we are to just simply balance a nuclear reaction. So if I look at this, all I need to first understand what is alpha particle. The alpha particle is basically the alpha particle. So we want to find X. The alpha particle is basically a helium particle. Okay, so I have 4, I have 2. So in the helium particle, all I need to find is a balance. This is 226. Okay, 86 plus 2, that is 88. So all I need is to subtract 226 minus 4. And of course, x will give me 222. So that solves that. So I just need to balance the atomic number and the mass number in this situation. Once I can identify what an alpha particle is, then I can solve this one easily. So the question is, what is the shape of ammonia molecule? What is the shape of ammonia molecule here? So to solve this question, we need to have an understanding of how ammonia molecule is solved. So this is ammonia. Of course, ammonia has, in its outermost shell, it has 5 electrons. So if ammonia should react with hydrogen, hydrogen is sharing one with one of the molecule, sharing another one, here, sharing another one here. So when I have this, these are bond pairs of electrons. I have only one lone pair. So basically, if I draw this is what I'm having. And a lone pair. So basically, to do this, we use the idea of lone pair to understand how many bond pair of electron do we have. So we have 3 bond pair, 3. So if it is 3 bond pair, then definitely our answer will be trigonal planar. If it is 2 bond pair, 2, like in the case of, in the case of carbon dioxide, we have a 2 bond pair of electron, then that is going to be linear, and the bond angle will be 180 degrees. Okay, so basically the number of pairs of electrons can determine what we have. So if I have 3 bond pair, then definitely I have a trigonal planar. The mass of silver deposited when the current of 10 ampere is passed through. So if you look at this question, there is a formula that could help us solve this easily without stressing ourselves. I call this formula one formula answer all. So this is the mass. We can use this formula, uppercase M I T over CF. So this should help us quickly. So what does this M represent? This bigger M represents the molar mass. The bigger M represents the mass, the molar mass. So if I have to do this, the molar mass of silver is 108. I'm having 108 times, what is the current? 10. Okay, times what is the time? 4,830 seconds. So I'm going to look at what is the charge on silver. What is the charge on silver? So silver is Ag plus. So that is only one charge. I use this one to pick. So that is 1 times Faraday. We'll be given the Faraday to be 96,500. So that is 96,500. So if you press this in a calculator, definitely we'll have a 54.0 gram. So that's 54.0 gram. If you press this, we have 54.0 gram. Okay. Tin is unaffected by air at ordinary temperature due to what? Okay. Of course, we know that is unaffected by air. That is due to its weak electropositive character. It has a very weak electropositive character. So that means it's not very reactive. Okay. So the moisture in air, that is water vapor in air, will not affect it at ordinary temperature because of its low reactivity. You know that we have hydrogen is higher, it's way higher, okay, than tin. So because of this, We still have copper, silver, like that. So we're not going to have, because of it cannot displace hydrogen. So it will not be affected, by air at all. Calculate the amount in moles of silver deposited. So this is like the question we just solved. We have to calculate the amount in moles of silver deposited when this. Okay, so what do we do here? 1 mole, this stoichiometry, 1 mole will be 96,500 coulombs will discharge 1 mole of an element, any element, or say 1 mole of an electron. So 96,500 would liberate that. So for me to know the number of mole that 9,650 coulombs will discharge is for me to just find S. So I can cross multiply like this. Don't forget 1 mole, 1 Faraday discharges 1 mole of electron. If it is not silver, we can use the second law to know that number of mole is inversely proportional to the electron charge. But in the case of silver, it's going to be 1/1. So that's why I can have that 1 mole easily. Okay, 1 mole of electron will be discharged in the case of silver. So in the case of, if it were to be copper, it's not just going to be 1 mole. It's going to be 1/2 mole. 97,500 coulombs will liberate 1/2 mole. But since silver has only 1 mole of electron discharge during electrolysis, so 1/1 is still 1. All right. So having established that, we can find what S is by saying that X is basically 9,650 divided by 96,500, and that should give us 0.1. 0.1. So in the next question, the reaction of halogens with alkanes in the presence of sunlight is an example of what? The reaction of halogens with alkanes in the presence of sunlight is an example of what? Okay, so we know, let's look at alkanes. Alkanes are saturated hydrocarbons. They are saturated hydrocarbons. So because they are saturated, we already know the type of reaction they can go. They cannot undergo addition reaction. They're already saturated. Okay. Oxidation reaction is also an addition reaction. Remember, addition of oxygen. Okay. Hydrogenation is also an addition reaction. So definitely the reaction that saturated hydrocarbon undergo is substitution reaction, where you have, if I have something like this plus chlorine in the presence of sunlight, okay, and we have one of the hydrogens substituted. One of the hydrogen is substituted, and I have HCl. So when I have something like this, where one of these hydrogen from here is substituted by the halogen, chlorine, then definitely, excuse me, so definitely what I have here is hydrogenation or substitution reaction. The enzyme used in the hydrolysis of starch to dextrin and maltose is just an information question. So you can always check this kind of information. Is amylase. Hydrolysis is when you break down. So when you break down starch, you break it down to give us dextrin, okay, plus maltose. This will only happen under the enzyme amylase. The alkyl group is represented by the general formula what? The alkyl group is represented by the general formula. Okay, so let's pick this one. This is the general formula for alkene. Okay, this is the general formula for an alkyne. All right, this is the general formula for an alkane. So that basically gives us the option quickly. So alkyl group is basically when you knock out one hydrogen from an alkane. What is this change in the oxidation number of copper in the reaction? So let's bring it out. I'm having copper, this 2, changing to copper. Okay, so let's find the oxidation number of copper here. Don't forget that since it doesn't have a charge, the total oxidation number is going to be equal to 0. So if it's equal to 0, I'm looking for copper. So 2 copper, applying the information we have used before. Sulfur is in group 6, so its oxidation number is going to be -2. So that is -2 equals to 0. So 2 copper will be equals to 2, and then copper is going to be equals to 2/2. So the oxidation state here is +1. Since copper here is in a free state, so its oxidation is going to be 0. So that is +1 to 0. So I may want to ask, is that oxidation or reduction? Okay, you think about that. So this, you have to calculate the mass of copper deposited when the current of 0.5 ampere was passed through a solution of copper 2 chloride for 45 minutes. So the only difference from here is the time. We still apply the same formula we've used, but in this case, the time needs to be worked on. So the time, since time must be in seconds, so I'm going to have 60 times 45. 60 times 45, that is the time. So apart from that, we are still applying the same formula. M is MIT over CF. Okay, so that means my M is going to be, what is the molar mass? That's 64 times the current is 0.5, so times 60 times 45, that represents the time, everything. So what is the charge on copper? We know that copper has a 2+, so they've also given us as copper 2. So if it is copper 1, then the charge is going to be 1, but since it's copper 2, it's going to be 2. So that will just be 2 times the Faraday, 96,500. So we could solve this easily by using our calculator. If I do that, I'm going to have 0.448. So that gives us the option D as our answer. So we have to find the IUPAC name of this substance. How do we find IUPAC name? We find IUPAC name basically, number 1, to identify the longest chain possible. So in this case, I can find the longest chain, that is 1, 2, 3, 4. That is the longest chain possible. And of course, I can have it here 1, 2, 3, 4. So why am I numbering from here? The functional group plays a role because there's a functional group present. That's why my numbering starts from 1 here. I could have started from 1 from here, but since the functional group plays a role, so I'm starting from the functional group 1. So this is an attachment. I'm saying this as an attachment. Since it's not part of the long chain, any element, substance that is not part of the long chain will be treated as an attachment. So it's attached. And since it has only 1 carbon, this is a methyl. Okay, corresponding to the alkyl group. All right. If something has 4 chain, we know that that is a boot. It has carbon 4, that is a boot. But since there is a functional group present, what is this functional group? This is an ene. So definitely I'm expecting a butene. Okay, so let's put this together. We've established that the surname is a butene, but there's a so this basically a but1-ene, because why a but1-ene? But1-ene because the double bond is attached at the first carbon. So at carbon 1, I have a double bond. Okay, you want to say, what of carbon 2? We always pick the least number possible. The least number possible. So I have a but1-ene, but what of the attachment? Where is it attached? This attached substance is at carbon 2. So that solves it basically. So I have the surname, then I can have the other name to be what? 2-methyl, because methyl is attached at carbon 2. The double bond is at carbon 1. So this corresponds to this 2-methyl. So we can have a 3. That is 2-methyl but1-ene. 2-methyl because the attachment is at carbon 2. A 1-ene because the double bond is in carbon 1. And a but because, of course, I have the longest chain to be 4. So I use this basically, this can help you. MEP-B. MEP-B. If you're having one carbon chain, that is a meth. Meth. If you're having 2 carbon chain, that is an F. If you're having 3 carbon chain, that is a prop. If you're having 4, that is a but. Of course, the other ones, you can use the idea of a polygon. Okay, so if it is 5, an angle with 5 sides, they said this is a pentagon. So that would be a pent. If it is 6 hex, okay. If it is 7 heptagon, hept. So that goes on and on. Now the functional group will now determine the last name it's going to have. The reddish brown rust on iron roofing sheet consists of, so I've actually made mention of this when I solved the question on rusting. So the reddish brown, okay, when iron rust, we've mentioned that what is responsible in air is basically oxygen and water. So an ion in its oxidation state of rusting is ion 3. So basically C corresponds to that. So why do we put SH2O? That is to indicate that we cannot really determine the number of water molecules. So since we are talking about roofing sheet, we cannot really pick particular water molecule that is being added. So SH2O. The density of 2 gases, S and Y, are 0.5 and 2.0. We have to find the rate of diffusion. What is the rate of diffusion here? So basically, let's pick X, Y. Okay. Now, X is 0.5. This is 2.0. What we want to find out here is which one diffuse faster and to what ratio. Because it's a relative, so it's a ratio. So if I'm going to find the ratio, I'm going to divide by the smallest. 0.5, 0.5. So this ratio 1 to 4. So definitely, relation of X to Y means that X will be 4 times faster than Y. So definitely, that is a 4. 4 times faster than Y. Since it has the lowest ratio, of course, if it has the lowest ratio, lowest volume, lowest mass, you expect it to be faster. Rate of diffusion. Don't forget what Graham's law states is that the rate of diffusion is inversely proportional to the square root of the mass or density. The carbon atoms on ethane are what? So let's look at what is ethane. So this simple, this ethane. Okay. So if you look at this maintain the tetravalency. So if it's maintaining tetravalency, let's look at what is the excited state of carbon. The excited state of carbon give us something like this. I'm going to use the Hund's rule to solve this. So I have a 1s in the excited state, a 2x, and a 2p. So this is not a ground state configuration. The excited state, you have this, 1, 2, 3, 4. Okay, so basically, if I have carbon like this and hydrogen is trying to form a bond with it, it will be because the hydrogen is filling up here. Since I'm having 4 hydrogen, one of the hydrogen is filling here, another of the hydrogen is filling here, another of the hydrogen is filling here, another of the hydrogen is filling this place. So basically, we are saying here that an s orbital is involved and 3 of the p orbital is involved. So this makes it sp3 hybridized. sp3 hybridized. If you were to be an alkene would be sp2 hybridized, while an alkyne would be sp hybridized. According to Charles' law, the volume of a gas becomes 0. Of course, Charles' law has proved that gases are not freeze at 0 degrees Celsius like water. They are not fizzed. So that will only happen at minus 273 degrees Celsius. Okay, what you call absolute temperature. All right. An oxide SO2 has a vapor density of 32. What is the atomic mass of X? How do we solve this? Remember that relative molecular mass is equals to 2 times vapor density. All right. So all I need to find is, let me find the relative molecular mass of SO2. So for SO2, that will be 2 times 32, and that will be 64. Okay. But that is not our final answer because they are not asking us for the relative molecular mass of SO2. They want us to find the atomic mass of X. So if SO2 is equals to 64, I can find X by saying X plus 2 times 16, because the atomic mass of oxygen is 16 equals to 64. All right. So definitely, if that should be the case, X plus 32 will be equals to 64. So X will be 64 minus 32. 64 minus 32. So of course, we have 32 there. The gas that can be collected by downward displacement of air is what? The gas that can be collected by downward displacement of air is what? So how do we do this? We do this by looking at how dense a substance is. How dense a substance is. Okay? How dense do we have this substance? Okay, so which one? We look at chlorine is lighter. If it is lighter, it's going to be by upward displacement. Sulfur dioxide is lighter than air. Carbon dioxide is lighter than air, but ammonia is denser. So what we are saying is that if it is downward displacement of air, okay, something that is denser comes directly in, okay, because being denser will make the air to be displaced downward. So ammonia will be collected by downward displacement of air and upward delivery of tube. Upward delivery. All right. A particle that contains 9 protons, 10 neutrons, and 10 electrons is what? A particle that contains 9 protons, 10 neutrons, and 10 electrons is what? So let's look at this particle. We know that the number of proton and electron are expected to be the same for a neutral atom. So if this particle has gained an extra electron, because if the number of proton and electron are not the same, meaning that it has gained or it has lost an electron. So in this case, it has gained. So if it gained an electron, you expect that you are going to form a negative ion. You have to calculate the amount in moles of a gas which occupies 10.5 Dn³ at 6 atmospheric pressure and 30 degrees Celsius. So basically, if I'm going to do this calculation, I'm going to use the ideal gas equation. The ideal gas equation is PV nRT. That is the ideal gas equation. So basically, what I'm looking for is the N, which is the number of moles. All right. So N will be PV over RT. Okay. The P stands for pressure, that is 6. The volume, the V stands for volume, that is 10.5. Okay. All right. That's 10.5 over R has been given is a constant 0.082 times the temperature. Now we may need to convert, since the unit of the R shows that R is a Kelvin, so we have to convert the 30 to Kelvin. So the temperature is going to be 30 plus 273. So that will give us 303. So that is times 303. So we could press this in our calculator quickly. So that gives us 2.53. So 2.53. That makes the right answer for that. Now in this question, if 100 of oxygen pass through a porous plug, okay, they want us to find the time that the same volume of hydrogen will pass through. This is basically using the Graham's law of diffusion. In Graham's law of diffusion, we know that R1 over R2 equals, vapor density D2 over D1. That's Graham's law of diffusion. So in this case, what is rate? All right, rate R is volume over time taken. So rate is volume over time. So we may need to find the rate of oxygen first. That is, the volume is 100 over time 50. So that will be 2. Okay. So we are saying 2 centimeter per second. If you are to find the rate of hydrogen, hydrogen is 2. So basically, this will be, since it's the same volume, 100 over T. Okay. So we can establish the rate quickly before we move to the density. Okay. What is the density of, and we may decide to use the mass. The density of oxygen will be 16. Okay. Because since we know that is RMM over 2, that will be 32 over 2. 32 over 2. So that is 16. That of hydrogen, GH2, will be 2 over 1. No, 2 divided by 2, since RMM is over 2, so that is 1. Having established this, then we can say, applying this formula, we can say that 2 over 100t equals the square root. Okay, don't forget 2 is for oxygen. So to make this easier, just looking for a way to make this easier for us. So for easy manipulation or easy calculation, we can decide to put hydrogen as our R1, so 100 over T, everything over 2 will be equals to square root, so that I can have that of oxygen 16 over 1. So that makes the work very easier for us. So such a way that I now have 100 over T, okay, times 1 over 2, everything equals to 4. So if I solve this, this is saying 100 over 2t equals to 4. So 8t equals to 100, and t equals to 100 over 4. 100 over 8 rather. And if you do 100 over 8, that should give you 12.5. All right. Don't let me bore you with the mathematics part of it. What is much more important is that I need to apply this formula to solve. You can use any mathematical manipulation. So I have R1 over R2, square root of D2 over D1, or M2 over M1. Either the formula that I use, I'm going to get the same answer. And the fact that rate has to, anything that has to do with rate has to do with time. That is volume over time taken. So if you apply this, apply any form of mathematical formula, you still get your right answer. So thank you for today's session. We've come to the end of today's session, where we have been able to solve some past paper questions. You can check our other videos for further explanations on some of topical questions. Thank you.